Hi everyone. I'm going to present our participation in the third track of BioCreative VIII shared task entitled Recognizing and Normalizing Continuous and Discontinuous Genetic Phenotypes using T5 variants and sentence transformers models. This task is focused on extracting and normalizing genetic phenotypes from dysmorphology physical examination reports. Participants were provided with patient physical examination entries that may include normal findings, key findings, or no findings. Participants have to perform two tasks: extract key findings while neglecting the normal findings, map the key finding to their respective human phenotype ontology identifier. For the dataset, we have de-identified short reports of clinical observation noted during dysmorphology physical examinations. The corpus contains a total of 3,136 observations split into training, validation, and test set. The task organizers stressed the importance of solving the problem of disjoint mentions, which constitute around 14% of all entity spans. Let's see what do we mean by these disjoint mentions. In the dataset, the disjoint mentions appeared in several forms. For instance, we can see some spans of non-consecutive tokens, where one entity is interrupted by one or more non-entity tokens. Other form is when spans share a common head, where two or more entities share a common token and one entity interrupts the other. Our model is called DiscHPO, which has two components: a sequence-to-sequence named entity recognition model based on several variants of T5 to recognize both continuous and discontinuous mentions on the sentence level. For the NER model, we have utilized the low-rank adaptation LoRa approach for the extra-large pre-trained models. The second component of our model is an entity normalizer, which is underpinned by sentence transformers. It includes BioEncoder for candidate generation and a Cross-Encoder for re-ranking. This is our model architecture. This architecture includes two phases, where the first phase includes the spans extraction. A pre-processing step is undertaken to convert the numerical offsets of the spans into the actual word spans, and each span is then prefixed with the entity type. We utilized several T5 variants, such as the original T5, Psi5, Flan T5. For the second phase, it includes linking the extracted spans into their respective human phenotype identifier or HPO identifier. Here, we utilized the sentence transformer framework by using BioEncoders for candidate generations and cross-encoders for term re-ranking. Our results on the validation sets shows that the highest gain was obtained using Flan T5XL while optimizing LoRa with Alpha 1024. On the test set, we have submitted 3 runs to the competition. We applied the same normalization components on all runs while employing different NER settings. We used Flan T5XL and LoRa with different alpha values, where alpha is a hyperparameter used in LoRa. The best achieved results was when alpha is set to the value 512. We had a normalization F1 score, which is equal to 72%. This is our last table, which represents the results of discontinuous span extraction on the validation set. We can notice that Flan T5XL with LoRa alpha of 512 is superior in detecting disjoint mentions of findings with an F1 score of 62%. To conclude, we can say that our NER model can identify discontinuous spans to a certain extent. We also observed that in some cases, partial span extraction might be sufficient for normalization. In addition, when disjoint spans share a common head, each span must be resolved to its own head and its constituent tokens to avoid missing normalizations. Thank you and have a nice day.